It's about 100 degrees outside in New York today, so seemed like a good time to do a teardown on this new gradient window heat pump. This is the indoor unit, which we'll take a look at later, but first I want to take a look at the outdoor unit because that's where the interesting stuff is going on. The first thing you'll notice is these ports here, which tells us that this unit is circuiting coolant between the indoor and outdoor unit rather than refrigerant, which was an interesting choice. It means that everything's simpler because you don't have to have the refrigerant going out of this unit. It's completely sealed in here, but you do have to have a heat exchanger in here, which you lose some efficiency, both because there is a delta T across that heat exchanger and also because you can't move as many ATU through liquid as you can through a refrigerant that goes through a phase change as it goes around the loop. Looking at the top here, we see it's using R32, and this thing weighs 95 pounds, which I just carried it up the steps. It is a very heavy unit to have hanging outside your window. I'm surprised they went with such a big, heavy unit rather than a smaller size, which could have had a smaller price, but let's take a look inside and see what's going on. That was not too hard. If you're gonna take one of these apart, just know that you're gonna have to take that bottom plastic piece off first in order to get access to all the screws that hold on the cover. First, let's take a look at the controller enclosure where the controller boards are. Since it's right here, some nice wiring diagrams, and this just lifts off. Now, my first area of concern is that this is really not IP sealed. There's some foam gaskets here, but there are plenty of ways for stuff to get into that box. Most concerning is right here, where the wires go in through this hole. You can see it's just wide open, and I'm gonna make a prediction right now that within the next couple of years, they're gonna have some failures due to insects crawling in through this hole and making their home inside this controller box, which eventually is gonna short something out or cause some corrosion on some lines. Those insects, boy, they will, any hole you give them, they will use. Would have been better to fill this with some kind of foam or something just to keep them from getting in. You don't want to hermetically seal this box unless you're going to fill it with nitrogen, because then you'll have problems with condensation and pressure equalization between the inside of the box and the outside of the box as temperature changes. But you can put something in there to try and block the insects from getting in. This giant board here is the inverter. This board's job is to drive that compressor motor, and it takes 120 volt AC running at 60 hertz in on this side, and it sends out 350 volts on 3 out of phase sine waves coming out, and the frequency of this is variable, so it'll change the frequency to change the speed of that compressor motor. That's the entire job of this giant board here. It's a pretty standard board. Some compressors come with them. I don't know if Gradient made their own or they used one of the reference designs, but it's pretty straightforward. Interestingly, these 3 lines here are safety lockouts. Those come from 2 overpressure switches and 1 freeze lockout switch, and they go onto this little daughter board. And if any of these lockout switches trip, it cuts power to the compressor. And the reason you want to do that is because if you have too much pressure running in the high side over here, it could damage the compressor and maybe even blow out one of these connections. And you don't want to do that. And so here are those 2 pressure sensors. I don't know why they used 2. It might just be a safety thing where if one of them fails, they want the other one to trigger. But really, you would expect the pressure that these 2 guys are seeing would be the same since they're connected by this tube. The freeze lockout is buried in here next to the heat exchanger, which is this block here. And it's hopefully set to trip before you get down to the freezing temperature of that glycol. And the idea behind that is if that glycol turns to ice, it's going to expand and it's going to pop this heat exchanger and cause leaks. On the glycol side, it would just be a big mess and it'll ruin the heat exchanger. But on the refrigerant side, if you start leaking that R32, again, you could possibly have a problem because it's highly flammable. Let's see, I don't know why this darter board is separate. That might be a standards requirement that it just has to be on a separate board to pass. This giant flat cable here is just the communication path from the main controller brain board to the inverter. And really the only important thing that runs over this cable is the brain board telling the inverter what speed to run that compressor at. There may be other diagnostic information in here, like it telling the main brain if there's any problems. But really, I don't know why they picked such a huge cable with so many conductors. Really could have gotten away with 2 or 3 conductors using either RS-232 or CAN bus, since both of the chips on both of these boards directly support CAN. Would have been an easier way, but who knows? This is the main brain board. It has an ARM processor on it. This controls everything. It's taking sensor readings from all the temperature and pressure sensors, doing some calculations, and then driving the speed of the condenser fan and the coolant circulator pump. And it's also telling the compressor what speed to run at and trying to meet whatever demand the user has. It also controls the reversing valve, whether you're in heating mode or in cooling mode. And yeah, there's the little ARM chip that runs that, pretty standard STM32. Not a lot of surprises here. This is the 24 volt power supply that just makes the low voltage power for running this controller board, and also probably for some of those fans and some of those motors. Pretty straightforward stuff here, so let's dig deeper. So I'm sorry, if I really loved you, I would take off this back plate and so you could see all of the insides naked. But to do that, I would have to remove these hose clamps that hold the coolant line on. And if I did that, I would probably spill coolant everywhere, and I don't feel like cleaning up that mess today. So instead, I think we can see everything we want to see. It'll just be a little bit cramped. Starting with these connectors on the coolant lines. This is what connects the glycol in the indoor unit and the outdoor unit together going through your window. And these are amazing connectors because they don't leak any stuff in or out every time you click connect them. They're quick connects, so they will click on and then you click them off. Sounds like it would be an easy thing to do, but it's actually really, really hard to do. This one, the brand is SeriesLock, but I've also seen similar connectors to these on the Mr. Cool DIY units. In those cases, they use that quick connect for the refrigerant line, and I've had some of those in place for years, and they just don't leak. They're amazing. You don't feel like puff of refrigerant when you first connect it, and then years later you still have the charge in the system. It's pretty cool. This is a little bit of a concern here on this coolant line. This insulation does not go all the way up to the end, so this part is exposed to the constant flow of fresh air that's going to be going through here because of the condenser fan. And in summertime, you're going to have hot, moist air going over this very cold water, and you're going to get condensation forming on the bottom of this hose, and it's going to drip down all over on this stuff in here, on this reversing valve and on this solenoid. And anytime you have something that's just constantly wet like that, there's going to be problems. You're going to get like slime mold and stuff on there and corrosion. Eventually, I think it's going to cause problems. So I'd much rather see this insulation go all the way up to here, and you get a little tiny bit of a bump in efficiency because you're not heating up this water. This is the reversing valve. This is what makes it so that this can be both an air conditioner and a heater. And if you don't know how these work, what's going on inside there, you should Google reversing valve, because it's really an amazing mechanism. It took them a long time to figure out how to make this so that it could do it while also being completely sealed to the outside so it never leaks. These are those two overpressure switches that safety out in case the pressure in the high side gets too high. These are just switches. They either trip or they don't trip. But we also have these pressure sensors. This one's on the high side and this is the low side. These are telling the controller what the pressure in these lines are so that it can make adjustments to how it runs all the different fans and the speed of the compressor to get maximum efficiency to meet whatever your load is. This is the accumulator. This basically just keeps liquid refrigerant from ever getting into the compressor because that would kill it. And it also can accumulate some refrigerant in here for when you, because of the temperature, you have more liquid refrigerant than gas refrigerant in the system. These foam blocks here just prevent some of the vibrations from this compressor from getting up into the rest of this piping. So it keeps everything from rattling around. In there, you can see the fan that's blowing over the condenser coils. Kind of interesting fan. So it runs on 120 volts, but it has a digital pulse width modulation line that goes up to the controller. And so the controller changes the duty cycle of that PWM signal to change the speed of that fan. If you have ever built a PC, you probably noticed that those fans work the same way. The one on your CPU cooler, your motherboard is changing the PWM. So that means that that fan has its own little brushless DC motor controller inside of it, which is, I guess, a good choice. But interesting that they didn't just have a BLDC motor on there that's directly controlled by the controller. All right, up here is a very interesting thing that I like. This is the condensate line that comes from the indoor unit, and in air conditioning mode, you're gonna have a pump in the indoor unit that's pumping that condensate water up into this hose, and then this drips it down onto the condensing coil. This is great because it means this condensing coil in AC mode is gonna be hot, because you're gonna have the hot gas flowing through here. So that condensate is gonna drip on this hot coil, and it's gonna evaporate because you have all this air blowing through and it's hot. It's just gonna evaporate and be gone. So you don't have any dripping condensate under any conditions, which is great. And some places actually require you to have condensate management like that. Notably the New York City Housing Authority, which I think that they're trying to get this unit into, so they really had to do that. I do think you take a hit on efficiency though. I think it's slightly more efficient to use that really ice cold condensate water to subcool the refrigerant as it comes out of the condensing coil, but I'm not sure about that. If you know the answer, if you've done the calculations or really measured it, let me know. Curious to know which is more efficient. This is the circulator motor. This is a 24 volt brushless motor. It has 3 wires that go straight into that controller board. And so the controller can directly control the speed and the direction of this. And this is pushing that coolant glycol through that loop that goes between this outdoor unit and the indoor unit. Here we have a temperature sensor on the coolant line. There's another one on down here before it goes to the heat exchanger. And these are interesting because these to me look like they're automotive temperature sensors. That plug looks like an automotive plug, which would make sense because you have temperature sensors on the coolant line inside your car that's going to your radiator. So I don't know, maybe I'll get the part number and look that up and see if it's for cars or not. Going over this way, this is the other side of the coolant loop and the other one of those quick connectors. Oh, down here, you can barely see it, but is the expansion valve, and they used an electronic expansion valve, which is continuously controllable. And this is a pretty standard thing, but it's still cool. So this is the top of the expansion valve. This is coils like in a stepper motor, except sealed in potting compound. The controller energizes these coils in series, and by doing that, it makes a magnetic field that sort of rotates around through this donut. And then this donut fits on top of a little capsule that's sealed into the refrigerant system. And this is it, if you can see it, right here. And in there, there's a magnet. And so as those coils energize, the magnet in here turns, and that is turning the needle valve, making it go up and down and opening and closing the valve. So cool that this is completely sealed because the magnet is going through this head here. Those are cool. And then this honking chunk of metal right here is the heat exchanger. This is what makes this unit into an air-to-water heat pump, as opposed to an air-to-air heat pump like a normal air conditioner window unit would be. You have refrigerant goes into this, and refrigerant goes in one side and out the other, and then the coolant goes in one side and out the other, and it exchanges the heat. So in air conditioning mode, you're gonna have liquid refrigerant going in here and hot water, and then vapor refrigerant and cold water coming out, and then that cold goes into your house, and you use that to cool the air inside your house. These are pretty amazing things. I have a smaller one here, and the way it works is you'd have, say, refrigerant going in here and coming out here, and then coolant going in here and coming out here. And so the refrigerant is flowing one way and the coolant is flowing the other way. And if you see this is a stack of plates, every other set of plates, one set is refrigerant, then the next is coolant, then refrigerant, then coolant. So you have a huge amount of surface area for them to trade heat. The way they make these is so cool. They stamp out these sheets of metal, and then they stack them up, and then they put solder around the edges, and then they bake it until the solder melts, and then you have this big block of metal that's totally sealed with, it's just amazing. I'll put a link to one of the videos of how they do it. Next up, I think that's it for the outdoor unit, so we'll take a look at the indoor unit. Here's the indoor side, which is just a glorified fan coil. Here's the fan that is blowing air out into the room and sucking room air in through this coil, where it's either going to get heated and cooled depending on the temperature of the coolant that's running through these lines. Again, those really nice no leak click connectors. When this is in air conditioning mode, this coil is going to be cold, and you're going to have warm, moist air going over it, so water is going to condense out of it and drip down here into this condensate collection pan, which is normally underneath here to catch that water. And at the bottom of that pan, you have this little reservoir receptacle that the water is going to flow into it. And as it fills up, that little magnet's going to float and trip this switch here. And that switch goes up here to the condensate pump, which is going to turn on and pump most of the water out of this pan up through here and then out through that condensate connector, where it's going to go to the outdoor unit and drip over the condenser coil, as we saw before, which is going to cool it off and make it evaporate and go away. A bit of a concern here. This is really designed for use in a mini split where it would be sitting underneath the condensate collection tray and there would be a hose going in here. But here it's just mounted in the bottom of the tray. So that means that there's this gap between the bottom of the port and the bottom of the tray where there's always going to be about a ½ inch of standing water in the bottom of this tray. Anytime that you have still standing water exposed to air, you risk growing that slime, and that slime just causes so many problems everywhere in the whole system. It can cause things to get jammed and stuck and clogged. Another missed opportunity here is that since this pump is triggered only automatically based on that float switch, there's no way that they can trigger it from the controller. And in fact, I don't even think the controller can tell when it's been triggered. There's enough smarts in that controller that they could have done something, for example, like wait a few minutes until after you stop running the evaporator fan and then just run this pump prophylactically to drain out any water that has collected, even though it wasn't enough to trigger it yet. And that way you have the least amount of time of water sitting stagnant in this tray. You really can reduce the chance of growing that slime, or at least have less of that slime. Another missed opportunity, I would love to see a backup liquid sensor on the side of this tray that would tell the computer anytime this tray got too full. So if that liquid sensor ever triggered, that means something went wrong somewhere in this whole condensate system. Doesn't matter where, but whenever you see that, you just turn the whole thing off and show the user an error. Because if you were to keep running the system in that state, eventually you're going to fill up this tray and it's going to overflow and spill out. And if you have spilled out water going into the person's home, that's always a very bad thing, can cause a lot of damage. So it's worth the extra couple of pennies to put a backup sensor there. More connectors back here. This is the data connection that goes to the outdoor unit to tell it when to turn on and off and to get information from it. It's just an RJ phone plug, which probably was not a great choice for here. I probably would have picked something else. You can see that even though there is a gland here, it is not sealing well. You can see right through it, and so water will follow the wire into there, and this connector goes to the outside unit. So that whole thing is outdoors where water can get in there and mess it up. If they had used a CAN connector here, they have just some really, really nice IP rated connectors for CAN. It's perfect for that. If it can keep something sealed up tight on a moving car, it's going to do fine on an air conditioner. Plus, you already have CAN support in the microprocessor on the outdoor unit, and they already need to do some work to isolate that connection with an integrated circuit anyway. Might as well use a CAN transceiver. They're more modern and better. This is the power connector for the outdoor side. It's almost connected directly to the indoor power plug, except there is a relay over here that the controller can turn on and off to turn off the power going to the outdoor unit. But in a pinch, if you wanted to power the outdoor unit, you could connect your own plug to the outdoor unit. It's just normal 110 volt. You just would take away the ability of that controller to turn off the power to it. Another coolant line, you can see how long that is. They give you plenty of slack. There's a little zip tie for stress relief in there. It goes to this coolant reservoir, which is just like the coolant reservoir inside your car. You need this reservoir because the coolant is going to expand and contract depending on what temperature it is, and that's going to change the air pressure up here in the top of the reservoir. So you need this vent tube, which normally would be tucked into the case, just loose in there. There's this thing at the top, which I think is to prevent the coolant from splashing out or leaking out. Might be a check valve or a filter or something, but in my case it did not work because there was plenty of coolant that had spilled inside this case, probably from getting shaken around during shipping. I feel like the automotive industry also has solved this problem, come up with some way where you can let air in and out without letting any liquid go in and out. This is the motor for that linear fan, and then this motor controls some louvers that let you change the direction of the air coming out of the fan. Up here we have the main controller board, and its main connection goes out here to the user interface, which is just this knob. This knob has probably an optical encoder in it and some LEDs. This seems like way too many conductors. I feel like you could have done it with just 2 or 3 conductors by putting a little microcontroller in here, but whatever. This is very interesting here. There are these 2 little Bodge boards that have been soldered onto the main board, and they were populated with these little daughter boards, which look like they're DC to DC converters. So my guess is that after they designed this board and made a bunch of them, they discovered that they weren't getting the voltage that they needed right here. And so they made this little board to go in and take the place of a few components and cover their footprints and then fix that problem rather than spinning this whole board over again and having to reassemble a bunch of them. This is the main brain of the control board. It's an ESP32, cheap and very popular. There's lots of these in the world. Everybody uses them. It's nice because it has built-in Wi-Fi and Bluetooth, so this thing can stay connected to the internet and you can program it with your phone. Some dip switches here. I haven't seen dip switches for configuration since my US Robotics 28.8 modem, but maybe they added these as an homage to the HVAC industry, which holds on tight to the old school ways of doing things. Tons of LEDs, and all of this required these I/O expander chips. Really, I feel like you could have gotten rid of at least half of the parts on this board without any reduced functionality. And in fact, you would have had better reliability because every one of those pins can be a failure point. Every one of these ICs can be a failure point. And also, when you run out of any of these, all of a sudden you have a problem. You either have to redesign your board or source those. So less parts is always better. Another part that probably should go is this FDTI chip, which is likely connected to this USB port. I'm guessing it's a cookbook designed to let you program the ESP. I don't think you need to have that on this production board. You could just program the ESP once in the factory using either the JTAG socket or putting an ISP socket here. And then if you ever want to upgrade the firmware in the field, the user can just do it using their phone. There's plenty of OTA options, over-the-air programming options, to program these ESP32s. Again, this chip is protecting that serial interface. Probably would have been better to go with the CAN bus here. This one's interesting. It's a serial EEPROM. Do you know why they would put a discrete serial EEPROM chip on this board when there's so much non-volatile memory in this ESP32? Maybe it's to hold configuration information or a serial number or something. I don't know if there's a regulatory reason why that's required, but certainly it doesn't buy you any security because it's much easier to mess with this chip and remove it and replace it than it would be with this module. Once I have access to this board, I can get to either one of these easily. It's just so many LEDs. I don't know, my water heater downstairs only needs 2 LEDs to tell me what's wrong with it. And if I need more, I'm going to connect a debug connector anyway. This is very interesting. So you see these 4 plugs for NTC temperature sensors that are not populated. In fact, the only temperature sensor in the whole thing is this little board here, which has a relative humidity and temperature sensor. It's sensing the ambient air in the room before it gets to the coil. There's, as far as I can tell, no way on this unit that it can sense the temperature of the air blowing out into the room, which I think would be a nice thing to know, but maybe they put these here so that someday they can add it. Although again, I don't think I would have picked NTC. You can get those really nice DS18B20 sensors that only need 2 wires, and you can, just with those 2 wires, you can connect as many digital sensors as you want. They're cheap, accurate, and reliable. Yeah, I think that's it. So it's actually a really nice unit. Remember, this is a company that started from scratch, and this is their first design, and it fills a niche that really almost nobody else is in. If you need this unit, it's a great unit for you, and there's plenty of room for them to make it even better. So let me know if there's anything I got wrong, or if there's any questions or anything that I should have gone into more detail on.